Hello, this video is going over acid-base 6. That's our buffers practice problems. Okay, I'm just going to try and talk through these problems and walk you through the problem-solving process for these. So problem number 1, you've got a buffer made by mixing NH3 and NH4+. So you've got a weak base and its conjugate acid. And the question is, this would be a good buffer for around what pH range? And the rule of thumb is that the pH of your buffer should be within plus or minus 1 of the pKa of the weak acid component. Okay, so we're going to ignore this Kb value and just look over here at this Ka value, 5.6 times 10 to the negative 10th. The pKa is the negative log of the Ka. This is on your equation sheet. So you can go ahead and do this in your calculator and solve for the pKa. But if you look at your answer choices, before you get ahead of yourself here, your answer choices are not super precise. We just want a rough estimate of what this pH is going to be. So since my exponent is negative 10, the pKa is going to be somewhere between 9 and 10. That's how it works when we deal with these the negative log of things. So your pKa is going to be like 9-ish. So out of my choices, it seems like D is the most appropriate choice. You want something where the pH is close to the pKa. All right, number 2. Which of these would be considered buffers? So buffers, you need a weak acid and you need the conjugate base. And a general format would be weak acid looks like this, conjugate base looks like this. So if you take a look at these solutions, see what we have. HCl, this looks like an acid, that looks promising. And you've got sodium chloride, which is going to dissociate into ions. So you might be tempted to say, hey, this looks like a conjugate acid-base pair. And you'd be right, it is an acid and its conjugate base, but this is not a weak acid, this is a strong acid. And the conjugate of a strong acid is neutral. So this would not be a good choice there. Let's look at number 2. HF looks promising so far. Sodium fluoride is going to split up into the sodium and fluoride ions. Looks like we have HA and it's A-. And HF is in fact a weak acid. And this right here is the conjugate base. So yes, 2 is a buffer. And then 3 is the same as 1, where this is strong, so this is not actually a buffer. So it's only number 2 that's a buffer. Okay, so next page. A buffer solution is prepared by dissolving some solid sodium hypochlorite into a solution of hypochlorite. So you want to think about, okay, we've got this reaction here between hypochlorite and a hypochlorite ion and hypochlorous acid. Okay. The pH of the buffer solution is determined to be 6.48. So what do I know? I know the pH is 6.48. Indicate which is greater, HOCl or OCl minus in the buffer solution. So notice it's not asking me to solve for a particular number. It's just saying which is higher. But I do have to include some sort of calculation. Okay, so I have to show some sort of numerical work here. Let's see what else the problem gives me. It also gives me that the Ka is 3.6 times 10 to the negative 8th. Just from here, thinking about problem solving things. Some things you should think about. If you know the pH, that means you can determine the H plus concentration. So the H plus concentration is 10 to the minus pH. So that might come in handy later on. So these are just things you want to be thinking about. So I'm going to do that in my calculator real quick. 10 to the minus 6.48 is going to be 3.3 times 10 to the negative 7th molar. So that's my H plus concentration. You could also find the pKa. Maybe that'd be useful. There's a negative log of the Ka. And in this case, it's going to be 7.53. All right, so here's the things that I know over here. You might ask yourself, what can I do with them? Well, whenever they give you a Ka or some sort of K value, then know it's an equilibrium system. In this case, they give me a Ka, so it'd be helpful to write out what reaction that represents. It represents the dissociation of my weak acid HOCl. And I can write out a Ka expression for it. It would be H plus OCl minus over HOCl. So it's products over reactants. And if I were being asked to solve for a particular concentration, I might set up an ice chart and solve for X, but notice this is not asking me for that. This is just asking me for a ratio. So let's just look at this and plug in what we do know. So I do know the value of Ka, so this is 3.6 times 10 to the negative 8th. I do know the value of H+, this is 3.3 times 10 to the negative 7th. And then if I do that, it'll give me my ratio OCl to HOCl minus. Okay, so if I solve 3.6 times 10 to the negative 8th divided by 3.3 times 10 to the negative 7th equals your OCl minus over your HOCl. Whoops. When you plug this in your calculator, you find this is about 0.1. Okay, so the question is just asking me who's bigger, OCl minus or HOCl. Since this ratio is less than 1, that means this number on the bottom must be bigger. Okay. Another way in which you could think about this problem as well is you could say, so that's step one, you'd be done. Okay, here's another approach. You could say that if your acid and base concentration are equal, then pH equals pKa. But in this case, our pH is a little bit less than the pKa, meaning that your acid component is more concentrated. And you could also choose to back that up using, using the Henderson-Hasselbalch equation, pH equals pKa plus log A over HA. This would be another option always when you're doing buffers. You could always use this equation as well. So that's problem 3. So we know that the HOCl concentration must be bigger. Okay, so problem number 5. We've got a solution that's made by dissolving some potassium acetate in a solution, and we're given a Ka value. So I've got potassium acetate, I've got acetic acid, I'm given a Ka value. Okay, so let's see what the question is asking me for. First, find the concentration of acetate ion in the solution. So we want to look here, I'm adding potassium acetate. When I put that in water, it's going to dissociate because it is a soluble ionic compound, and it's going to make the acetate ion. So to figure out the concentration of the acetate ion, I have to figure out how much acetate did I add, and what volume did I put it in. Because remember, I'm looking, when it asks for concentration, it asks me for molarity, and molarity is moles over liters. So my goal, figure out my moles, figure out my liters, so I can find molarity. Okay. So first let's look at the moles. I've got 1.786 grams of potassium acetate, C2H3O2. I'm going to look up the molar mass of that thing. And I think that when I do that, the molar mass is 98.1 grams per mole. So you divide mass by your molar mass and you will get 0.0182 moles of your potassium acetate. And then my volume is 0.750 liters. So moles divided by liters equals my molarity. So the key thing to keep an eye out for, especially in these like AP release type problems, is some of these steps are going to be relatively straightforward. So like they might be kind of throwing in a, do you know how to do a molarity calculation in the middle of a question that's otherwise about acids and bases. So don't overcomplicate stuff. Sometimes it's as simple as taking the moles divided by liters. So it could be a really simple step happening. So that's my answer for A. I'm just trying to find the molarity of the acetate. And then find the pH. Okay, now I'm trying to find pH. And notice I'm given a K value. So whenever I'm given a K value, I'm going to say, hey, this is an equilibrium system. So I'm going to try and write out my equilibrium reaction, set up a nice chart, write a K expression. So those should always be your problem-solving steps that you do. So I'm going to write out the reaction for the acid. So there's my acetic acid. It is going to dissociate C2H3O2 and make this anion. And I can write out a Ka expression for this which is products over reactants, so C2H3O2. And here's my reactants, or my acid. And then I know, all right, I know the value of this. The value of Ka is 1.8 times 10 to the -5. This was given to me in a problem. And then let's look at like setting up our ice chart and see what else we're told. Okay, so look at this. We just figured out here that this is the molarity of the acetate ion, which if I write out the formula, that's this ion right here. So initially in my solution, I have 0.024 molar acetate, because this is how the solution is originally made. Okay. Do I know anything about my acetic acid? Well, let's go back to the problem. Am I given another molarity? Yes, I am. Okay, this is 0.345 molar acetic acid. Do they tell me anything about my hydrogen concentration? Nope, that's what I'm trying to find. So I'm going to assume it starts out at 0 initially, and I'm going to say X, 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 okay, 0.345 minus X, then X, 0.024 plus X. Okay, and then we're just going to take these and plug them into our K expressions. Remember, the whole point of the ice chart is to organize your information so that you can plug the appropriate values into this K expression. And I'm going to assume that K is small enough where I can make that approximation that 0.024 plus X is basically 0.024, because I'm just about small enough with my K value for that approximation to work. Okay, and then you go through and notice that when you're doing a buffer, when you're solving for X, the math I think is actually a little bit easier. So it's 1.8 e to the -5 multiplied by 0.345 divided by 0.024. Notice I don't need to do a square root at all. 0.000 I guess I'd say 26 here, round it up because this one has 2 sig figs, and then I'm going to take the log of that value, and that will give me a pH of 3.59. Okay, so yeah, there you go, and this is our, and make sure we answer the question. The question asks us for the H plus concentration and as well as the pH. So again, notice a buffer, it's just like any other equilibrium system. Write out the reaction, write out the K expression, plug in the values, and solve for X. Alright, I'm going to split this video up into 2 and make a second video that covers the last couple of problems.